Here in lesson 6, we want to talk about infinite limits. And I know we said before that if a function is going to infinity, what do we say? It does not exist, okay? But it still can be useful to recognize where the function is going, whether it's a positive infinity or negative infinity, okay? And then this is also going to allow us to recognize, as we'll see later, the asymptote, okay? We're going to look at vertical asymptotes. We'll even mention horizontal asymptotes a little bit, okay? So let's run through a couple of different examples here. These actually should go relatively quickly because you've graphed stuff like this in pre-calc honors, okay? So it says the limit of f of x is equals 3 over x minus 2 as x approaches 2 from the left and from the right. So that's what we're trying to find. Limit of 3 over x minus 2 as x approaches 2 from the left. And then also
I read that as just like 2.
this from the right. Okay? So, how do we sketch this?
It can't be a hole in 2.
It what? What about a hole?
Oh, it's not 2. All right.
Okay, x cannot equal 2. That's correct.
But it's not a hole though, because now it cancels out that hole.
Okay, it doesn't cancel out. So you're right, it's not a hole, it is an asymptote, okay? So if we're sketching this, and again, you should be able to make rough sketches like this. Here's our asymptote at 2. Now, that's the vertical asymptote. There's also a horizontal asymptote.
At 0. Right?
At 0, yes. Okay? It's at 0. Can someone explain how we know it's at 0?
Bobo bottom?
Alright, yeah, if you remember Bobo Botten,
Yeah.
if the degree of x, which in this case, the degree of x is 1 on the bottom, and in the numerator there are no x's, so the degree is 0. Okay? So, I have a bigger degree on the bottom, so therefore the horizontal asymptote is x equals 0. Okay? So vertical asymptote.
And no, it's 2 because it can't equal 2.
Correct. The horizontal asymptote is y equals 0. Okay? So now, you guys should understand what a hyperbola looks like. Okay? So we know that typically a hyperbola will have either a part here and here, or a part here and here. So how do we figure it out?
You graph it on. You plug in some 20s.
Yeah, plug in a point. Let's plug in a 0 for x. What do we get when we plug in 0 for x?
Negative 3 over 2.
A negative 3/2. So that means I have a point here, which means this whole thing, that tells me that this thing is going to look like this.
Yeah, which probably means the other one's going to be the other one.
Exactly. Unless you've got some squares in there or something like that, it's going to be diagonal from each other like this. Okay?
Doesn't that mean that the approaches from the left would be negative infinity and approaches from the right is positive infinity?
Okay, there we go. So the limit is going to approach from the left a negative infinity, and from the right it's going to approach a positive infinity. Now for both of those we still would say the limit does not exist, but here what we're doing is we're recognizing what's actually happening. Okay, it's one thing to say, oh, there's an asymptote, the limit doesn't exist. True, but we still may want to know, okay, well, it doesn't exist, but is it going to positive infinity or negative infinity? And this will help us figure that out. Okay? Another thing that we can do is we actually can find the limit, this was not asked, but the limit as x approaches infinity of 3 over x minus 2.
Isn't that 2? So that would just be 0.
Well, let's think about this. If we are approaching positive infinity, the further to the right we go, what's happening to our function?
It's going closer to 0.
It's going closer and closer and closer to 0. Good.
0, but doesn't exist still.
No, that
would exist.
that actually would exist because it's x that's going to infinity. As x continues to get huge, our function is approaching a specific value. It's approaching 0. Does it ever reach it? No. But it's approaching 0. Okay? Alright, so as we saw in this one, as x is approaching negative infinity, it's also approaching 0. There are functions out there where you might have two horizontal asymptotes. And as you go to positive infinity, it's approaching one value. As you go to negative infinity, it's approaching a different value.
Because they're.
Those are not standard rational functions like we looked at in pre-calc honors. Those would be a different kind of situation.
But that can happen when there are two horizontal asymptotes,
Yeah.
but how is this supposed
The function doesn't look exactly like this. It looks very different.
I understand, but it's still bubble bottom though, right?
No,
Oh, okay.
no. You'd have to figure it out a different way. So. All right. Bobobotin is only for the rational functions as they were defined, where you have a polynomial in the numerator and a polynomial in the denominator. You look at you can do Bobobotin. Okay. Here's another example. Kind of similar. Determine the limit of f of x equals negative 1 over x minus 1 as x approaches 1 from the left and from the right. Okay, so limit x approaches 1 from the left, limit x approaches 1 from the right. Both of these we're doing the negative 1 over x minus 1 as our function. Okay? So, what does this look like?
There's 2 asymptotes.
Asymptote at 1. Okay, so here's 1
And another one
And
is
0.
and a horizontal at 0. Good.
and -1 over
Okay, if we plug in 0, you get negative 1 over negative 1.
that's 1.
So that means it's going through this point here, which means we've got it looking like this. Okay, and that means it's going to go diagonal to the other quadrant down there for the other half of our hyperbola.
How do you know if it's How do you know it's going that way though? Like this direction. We know that when you plug in x or 0, it's 1. But how do you know that it's not the other way around?
Well,
Oh,
we know it's diagonal because this is just a transformation of our rational parent function. Okay, it's been reflected across the y-axis and translated 1 unit to the right.
So the parent function will be just that same direction, but this is a little bit.
Parent function would be back to the left 1 unit, and then you'd have to flip it back over the x-axis. So, as x is approaching 1 from either side, it's going towards positive infinity from the left, which of course we say does not exist, and it's going to negative infinity from the right, which also we say does not exist. Now, like we saw before with horizontal asymptote, one thing we can say is the limit as x is approaching positive infinity, and also negative infinity in this case, is actually going to be 0. And again, that's because the horizontal asymptote, we are approaching 0 both as we approach positive infinity and as we approach negative infinity. Okay? Now, the last example is a little bit different because we've got this x minus 1 squared. So, as we look at this, we still have the asymptote at 1, and the horizontal asymptote is still at 0. But what does that square do? Well, the square, if we were to plug in 0 for x, we'd get negative 1 over 1, which would be negative 1. So we do see that this is going down to negative infinity on the left. Okay, however, with this square, it's kind of interesting. If we tried to plug in, say, 2 minus 1 is 1, squared is 1. So negative 1 over 1 is also negative 1. So we actually see this where we are approaching the limit as x approaches 1 from the left of f of x is negative infinity, which does not exist. But also the limit as x is approaching 1 from the right is going to negative infinity. All right, and I shouldn't be putting equals. I should be putting approaches, or is going towards negative infinity. Okay? Because the limit does not exist. But again, it's useful to recognize where it's going to. We have vertical asymptotes. Real quickly with these, where would the vertical asymptote be on 4a here?
X equals negative 1.
Yeah, x equals negative 1. That's a vertical asymptote. Okay? Over here for b.
X equals 1 and negative 1.
Okay? Notice the denominator factors into x plus 1, x minus 1. So x equals negative 1 is a vertical asymptote, x equals positive 1 is a vertical asymptote. Okay? You should, if you're asked for asymptotes, asymptotes are lines, so you should give the equation of the line.
Alright.
Okay? Part C, cotangent of x.
At x equals, set negative pi plus, or pi, I don't know how to say it because they would keep repeating.
Okay, so give me a couple of them.
So you have negative pi,
X
0
can't
pi.
equal 0.
Okay, x can't be 0, so there's an asymptote. X can't be negative pi, x can't be pi, x can't be 2 pi, 3 pi, 4 pi, 5 pi. So-
X can't equal 0
Can't
without pi.
equal to pi.
Plus
N
n
pi.
pi.
N pi.
Pi, yeah, n pi. We have an infinite number of vertical asymptotes here. Any multiple of pi where n is an integer. Okay? If n is an integer, any multiple of pi will give us a vertical asymptote. Okay?
How do you represent 0?
N is 0.
Oh,
Okay? And then how about D?
at x equals negative 2.
Okay? You factor these here. And what does the numerator factor into? X plus 4x minus 2. If you're shaky on your factoring, you need to practice, okay? You got to be able to factor here. So x plus 4 times x minus 2. don't jump to conclusions here. Don't just automatically say, hey, there's asymptotes at -2 and +2.
They can't.
Oh, okay.
This one cancels. There is a hole at x equals +2. There is a vertical asymptote at x equals -2. Okay? So those are the vertical asymptotes. And actually, this right here is what this is saying up above, where f of x over g of x, g of c is 0, and f of c does not equal 0, then x equals c is an asymptote. All right?
Why isn't +2?
Because there g of c equals 0 and f of c equals 0, that's a hole, not an asymptote. Okay?
Can you tell down to number?
So the last thing I want to mention here is the horizontal asymptotes. We mentioned Bobobatin, okay? Now, obviously that doesn't apply with cotangent. That was just when we had polynomials, all right? But like we saw above, when the degree on the denominator is larger, like on A here, we would have a horizontal asymptote at 0, okay? And the connection I want you to make here is that horizontal asymptotes, in this case here, the limit as x approaches positive infinity of f of x is going to equal the horizontal asymptote, okay, which in this case was 0, okay? Now, there will be certain cases where you may have more than one horizontal asymptote. That's not this exact style, this rational function. But for rational functions, the limit as x approaches infinity of f of x will be whatever the horizontal asymptote is. Okay? Over here on B and on D, the degrees of the numerator and denominator were the same. So what's the horizontal asymptote on B?
1.
Y equals 1, alright? So the horizontal asymptote is y equals 1. Hang on guys, we have a couple more minutes. Okay? So we would say the limit as x approaches infinity of f of x equals 1. Okay? That's what our function is approaching. It's approaching the value where the asymptote lies. Okay?
So for the